So hi everyone to this new edition of the Quantum Spain online series seminars. And yeah, today we have a very special one, which is going to be given by Richard Kueng, who is a professor in the University of Linz in Austria. And I believe Richard is going to tell us about some work and this topic of shadows, which has to do with quantum tomography, which has to do with, I think, a very big question, no? Which is, for us classical beings, how do we interact with the quantum world? And Richard's work, as he's going to show us, hopefully, has actually given us some nice new ways of thinking about this question and giving interesting protocols, and this is a very important question for quantum information. So yeah, we hope that, I think today's talk is going to be very enlightening for all of us, hopefully, right? Yeah, with this, I think that's all I had to say. So please, Richard, go ahead.
Hola, muchas gracias, Álvaro, por invitarme. Me encanta estar en España virtualmente, pero voy a hablar en inglés, si es ok, porque he perdido un poco de mi vocabulario científico. So yes, thank you, Álvaro. It's a great pleasure to be here. And today I want to tell you something about the broad scope of classical shadows, which is a new way of constructing quantum classical interfaces. And I want to keep this talk rather high level in order to convey the intuition and the motives behind the framework rather than the technical details. So this is an overview talk. If you have any questions, please don't hesitate to ask them already through the talk. In my experience, if you have a question, then maybe many others have as well, and you can help me to get my points across more clearly. But if you do so, please do write them in the chat. And Alvaro was kind enough to agree to interrupt me and ask a question on your behalf. Okay, so here's an outline of today's talk. I really want to give a motivation, which I call the quantum readout problem. I think it's a very, very fundamental problem in quantum technologies. Then I want to give kind of like a high level introduction to one way of potentially addressing this quantum readout problem. And I want to do it in a case study, kind of like in a very simple 4-qubit example, so that you can get the main gist. And then I want to quickly also highlight an experimental demonstration that we did together with ion trap colleagues at the University of Innsbruck, also in Austria. And then I must apologize. Is everything okay?
You're not just sharing your screen, if that's what you wanted to do. Right?
Thank you.
I should have realized earlier, sorry. I guess the outline should be in the screen. Yes, now, yeah, perfect. Yeah. Sorry.
Okay. And then I must confess that I decided on very short notice to deviate slightly from my original agenda, because I was very excited about the Physics Nobel Prize today, which is about artificial intelligence. And so the very last part is a bit about our vision here in Linz to maybe synergize and unify quantum technologies with artificial intelligence. And this is really new. I haven't kind of like given this type of overview talk so far, so please bear with me if it's not to the highest standards, but I think given today, it might be cool. Okay. So here is a broad motivation about what kind of like really fascinates and bugs me and many other people. It's the quantum readout problem. I'm very excited to be kind of like, let's say, in my 30s today, because quantum technologies and the way we think about quantum mechanics has changed drastically since I became a PhD student roughly 10 or 12 years ago. For the first time in basically forever, we now have medium to large scale quantum devices which can host, let's say, a couple of 100 qubits. They are not perfect, the runtime is limited, it is noisy, but we really have devices where we can control hundreds of qubits. But these devices don't work in isolation, but they're always coupled with a powerful classical computer. And I'm also very fortunate because today we have really powerful and amazing classical hardware, ranging from the laptop that allows me to give you this presentation up to huge server farms, how they are used for ChatGPT or machine learning. But still, these classical CPUs are very reliable, they're big, they're fast, but their computing potential is not limitless. So they cannot do everything. And the readout problem happens when we kind of like do something on a quantum architecture with a couple of 100 qubits and maybe want to process the data or learn something. Because if we want to learn something about the state of the quantum architecture after computing, we have to measure the qubits involved. And as you all know, quantum measurement is destructive and probabilistic. So you have to repeat this entire procedure many, many times in order to get enough statistics to actually answer the questions you set out to answer. And if you're not careful, this often comes with an exponential overhead, because the Hilbert space of an n-qubit system grows exponentially in the number of qubits. And for the devices of today, if we think about 100 qubits, the Hilbert space dimension is 2 to the 100, and this is out of the question even for the most powerful classical computers. So this is really a fundamental challenge, and this is the challenge that me, my team, and many other people all over the world want to address. And our high-level vision is to bridge this gap between quantum and classical, to really develop quantum classical interfaces that allows us to think in a truly hybrid fashion about computing devices that have both quantum and classical parts. And what is very important for me, and I think this is timely now, is that we treat all computational resources on an equal footing. We cannot just assume unlimited classical computing power to do whatever readout protocol we want. And on the other side, we can also not assume kind of like unlimited quantum power to use a quantum computer to do the readout for us. So it's really about balancing resources and finding a good compromise between quantum and classical algorithms in order to bridge this gap. And what we set out to do is to really use quantum effects to make the readout more scalable on the quantum side. We want to build in synergies with learning and statistics on the classical side. And we also prioritize implementability. So ideally, all the ingredients of our solution should be executable on today's faulty quantum hardware. And if we meet all these three desiderata, I think we have a really good shot at bridging the gap between the quantum and the classical realm and opening up synergy potential for everybody who wants to use a quantum architecture. So this is kind of like the high-level motivation. The quantum readout problem is what we want to tackle, and we want to tackle it with both quantum and classical computing tricks in order to get the best of both worlds. And this led us to the idea of classical shadows, which is one way to address this readout problem in a way that fulfills several of the desiderata I mentioned before. And in order to motivate them, I want to contrast them with the state of the art, the way it is traditionally taught how to learn important properties from a quantum mechanical system. And this is via the language of quantum mechanical observables that you might be all very familiar with. Usually, we think hard before we do a quantum experiment. What are we interested in? Then we phrase this in terms of an observable. And then this observable can be diagonalized by a unitary matrix. And we can interpret this unitary matrix as a quantum circuit or a quantum kind of like processing routine, which I call a specific rotation here, that kind of like rotates the quantum state in question into a basis where the observable is diagonal. Then we take data and then we do statistics. This is the standard way of doing things. It's tried and tested, but in its very nature, it's special purpose and it is sequential. By this, I mean, when I think about a new observable, I have to diagonalize it. I have to extract a new rotation or quantum circuit to implement. And if I'm interested in multiple observables, I have to do them one at a time, at least if they are not commuting. Okay? So this is kind of like the standard way of learning observables of an unknown quantum system. And classical shadows is an alternative viewpoint on that, where we use the fact that even if we find the exact unitary that diagonalizes the observable, we still have shot noise. We have to prepare the quantum system, then we measure it, then we get one number, and we have to repeat this many, many times in order to get enough statistics to get a good idea about the expectation value. Okay, so kind of like even in this special purpose unitary, there's a lot of prepare and measure and repetitions. And what we came up with a couple of years ago is an idea that might sound crazy, but we replace these handcrafted specific rotations for a given observable with a random rotation. By this, I mean, kind of like my analogy is kind of like Plato's cave allegory. It's kind of like a bit illustrated on the very right. I think it's instructive to view n-qubit system, large quantum systems, as intricate, very high dimensional objects with the serious limitations that us macroscopic beings can only ever observe crude, low dimensional shadows of the object. And what we do is we kind of like find the right rotation to rotate it in a way so that the shadow is what we care about. And then we start repeating this in order to get enough statistical data to denoise and get a good idea. And what we do in the classical shadow picture is something that might seem crazy on first sight, but we forget the observables and we just rotate the system randomly, kind of like we give it a random kick. And then we take one of these low resolution shadows, we take data, and then repeat the entire procedure, but with a different random unitary. So kind of like for each shot we take, we use a different random unitary. And why is this not completely crazy? Because if I choose each unitary uniformly at random, then in expectation, the limit of many repetitions, I will see every possible rotation. And this will give me full information about the underlying system in expectation. And this opens the door to classical Monte Carlo approximation. And this is one of the most powerful classical tools we have to deal with big data problems. There you also have a big, complicated object, and you approximate it with easier things that are randomly selected in a way that they converge to the true object in expectation. And this is exactly what we do in the classical shadow framework. And then you reap all the benefits of a classical Monte Carlo technique. This is kind of like a new way of approaching this problem. It is universal in the sense that you can approximate any observable, because in expectation we see everything, and it is also parallelizable. If I'm interested in 100 different observables, I can use these random rotations and shots to generate data, and then approximate all the 100 observables in parallel. And this kind of like opens the door for a lot of computational advantages when it comes to the classical data processing side. And I was really happy to learn, and maybe you saw that as well, that John Preskill, one of the co-inventors of this approach, we did that together back at Caltech, Robert Kueng, myself and John, won the John Bell Prize this year, in large part because of this. And rather than going into technical details now and bore you with Monte Carlo formulas and high integrals, I just propose that we do a case study where you will hopefully see the benefits of doing such a Monte Carlo randomized estimation approach as opposed to the traditional sequential specialized approach. And I chose a very simple example, namely 4 qubits and a simple circuit that prepares 2 Bell states. We entangle the first 2 qubits maximally, and we entangle the last 2 qubits maximally, but there's no entanglement or correlations between qubit 1, 2, and 3, 4. So in a quantum circuit picture, this would look like this, and this is the quantum circuit we run to prepare it. And now let's do some toy examples about learning or kind of like inversion of properties. And one of maybe the most important things you might want to do when you prepare this on a real device is to check the global fidelity with respect to the ideal target state you want to kind of like prepare, a quality measure of how good your architecture is at generating Bell pairs. And then the standard tried and tested way is implemented here on the right, where we come up with a circuit that diagonalizes the fidelity with the GHZ state viewed as an observable. And it's really just undoing all the gates. And then in the end, you check whether you end up where you started, whether you measure all zeros or not. And then you repeat this many times in order to get enough statistics to get a good idea about the fidelity. This is the standard way of doing this. And it's a good way and maybe the best way to estimate fidelity. But what if you want to know more? Suppose you're also interested in the ZZ correlations, so the computational basis correlations between qubit 1 and 2, then what would you do? You would run a different circuit, right? You would just measure the first 2 qubits, and ZZ correlations are diagonal in the computational basis, so you can just read it out. But it's a different circuit. And then you can do this many times to get good statistics. Now, what if I care about XX correlations? I have to do something else, right? I have to rotate the first 2 qubits into the X basis using a Hadamard gate, and then I can take my samples. Okay? But there's many two-body correlations I could check. I could be interested in the correlations between qubit 1 and 3. Then I would have to run this. XX, I would have to run this, and you get the picture. There's a lot of different specialized circuits to get all two-body XX and ZZ correlations plus the fidelity. If you keep track, you need 13 different readout protocols to determine the global fidelity and all 2-bit correlations in the X and the Z basis. Okay, so this is not difficult and it can be done, but it requires work. For each of the correlations, I have to come up with a circuit that diagonalizes it, and then I have to run it sequentially. So here is what we do with classical shadows. We prepare the same state. This is exactly the same. We have to prepare the same quantum system. But then we do these random rotations, and we do them on a single qubit format. So kind of like these blue boxes you can see here are now placeholders for a randomly selected single qubit unitary. And the single qubit unitaries we use are either the identity, Hadamard, or phase times Hadamard, which rotates us in the Y basis on the Bloch sphere. And we choose one of these 3 candidates at random, and then we take a single shot and we get an outcome 0 for the first qubit, 1 for the second qubit, and those are bits. And we also store a label of the random unitary we chose. X for Hadamard, Y for S Hadamard, and Z for identity. So this is one repetition of the experiment, and it gives us an array of n numbers, a trit and a bit. This is very efficient to store, and this scales to many qubits. Like if I had 100,000 qubits, storing this would not be a problem. Now the twist comes, what do we do now? We repeat this independently for, let's say, large capital T times. This is the number of shots we take. This is kind of like how we take data. And each time we choose different single qubit unitaries and store the arrays with the outcomes. This gives us now a data table with the number of qubits, many columns, and the number of shots, many rows. And this is what we call a classical shadow of the quantum system, because it carries information about the underlying statistics. Quantum mechanics produce these strings. And now we can use standard Monte Carlo techniques to process these strings. And we can do that in parallel for many different observables. For example, if we're interested in correlations of qubit 1 and 2, only the first 2 rows will be relevant. We can forget the rest. But we can use the same data to also learn something about correlations between qubit 3 and 4 by just looking at column 3 and 4 and 2 and 3. And so this is really kind of like one strategy where we run the experiment, generate new data, but as soon as a new data array comes, we cannot use a parallelizable computer to update many different observable estimators in parallel. Okay, and so this is the overall idea on how to kind of like achieve the same task as it was out before with the classical shadow framework. And the nice thing is it's completely detached from the things we actually care about. The data processing procedure is the same, with just the Monte Carlo, the actual approximation stage, has to be adjusted. And I think this is best illustrated with a small video that I prepared. And I will try to share that now. Can you see the video?
No, not yet.
Okay.
So you stop sharing, and then now we just see your
Yes. Can you see the video now?
Yes. Oh, yes.
So, sorry, I want to go full screen.
Yeah, you're on full screen. Yeah.
This is now kind of like a numerical illustration kind of what we simulated, the process I just told you on the slides, numerically for the same 4-qubit system, 2 Bell states, kind of like on qubit 1 and 2 and 3 and 4. And what you can see here is the global fidelity on the top left, the ZZ correlations on the top right, the XX correlations on the bottom right, and in the middle top center, you even see more sophisticated estimators like the purity, which tell you something about entanglement. And as you can see, while I'm talking, these curves are moving. And kind of like this illustrates that we kind of like let the experiment run in the background. And as soon as we get a new data point, we immediately update each of these estimators in parallel. And as you can see, kind of like this converges rather quickly. Kind of like the fidelity is now already close to 1, which is the exact value because we did a numerical simulation. The ZZ correlators also have already converged, and the XX correlators as well, all at the same time, taken from the same randomized data. And this is for the experts, at time scales and short scales, where the density matrix reconstruction viewed on the top or lower left is still complete garbage. Kind of like if you know how a tensor product of 2 Bell states looks like, the density matrix on the lower left is still rather far away from this. So you can estimate properties of a quantum system much, much quicker than the time and short scales it would take to reconstruct the actual density matrix, which is the traditional quantum state tomography way of learning these things. Okay. And I think while this video is running, it has already converged. It still goes on for a couple of minutes more. I think this is a great place to stop and ask for questions or comments.
So if you were to predict some of these properties from the density matrix that you get, you will get something completely off.
Yes.
Yes. Okay. That makes sense. Any more questions in the chat? There's nothing so far. Yeah, I think. Hi from Gael Sentis. Yeah. Hi, Richard. So why do we see drops in the fidelity periodically? In the video, I think. Yeah.
Yes, because this is in a very, very low short regime where it really kind of like depends which random unitaries we choose in order to get a good approximation of the fidelity. And whenever we choose a wrong one, it can hop us back a bit. So this is kind of like a feature of small scale statistics and the way the estimator works. Also, you can often, in this case, it wasn't so pronounced, but you often see fidelity values larger than 1, which indicates unphysicality, but that's also a feature of Monte Carlo estimation. So kind of like this is really, I would say, small scale behavior before you zoom in.
Okay, so there's another question. Well, Gael says thanks. And there's another question from Mani Sartaf. And the question is, what are the constraints on the observable that we're looking for? Because presumably we cannot choose completely freely the observable.
You can choose it completely freely. Everything, you can choose observables. And you can even choose polynomial functions or analytic functions. Kind of like what you saw in the video was also a plot that tracked the purities. Purities are not observables, they are quadratic functions. It is, however, a big question, and I want to talk, this is a good segue that allows me to maybe go on the next slide where you can see there's a payoff. You can do it for any observable, but some observables are more expensive than others. Kind of like what you saw here, things converged really quickly because I looked at local 2-point correlators. If we now envision 100,000 qubits and a very complicated entangled observables over all the different qubits, then first of all, it would be very difficult to run the classical Monte Carlo approximation because we have to kind of like somehow process the big observable. And the statistics you need in order to get a good answer might take much, much longer. But for a large class of observables, namely local observables, the convergence rate happens very quickly and much quicker than what you would anticipate. And in particular, it's independent or only depends logarithmically at worst on the number of qubits. So this is scalable. And we can, just by looking at the observable, we can give rather tight upper bounds on the short budget you expect to need before you have a good idea. But in practice, convergence happens more rapidly. I hope this answered your question.
Yeah, I
Can
think
you
so.
see the slides again now?
Mani says thanks. Yeah, so now we can see experimental demonstration.
Very good. So this was numerics, a small-scale numerical example that we prepared to just give you the main idea of what classical shadows do differently from standard kind of like direct observable estimation. This is just very quickly. I like to collaborate with the ion trap people in Innsbruck. Maybe you know Rainer Blatt's group. They built kind of like their own quantum devices there and are pretty good. And so whenever we have a new theoretical idea in Linz, we call our friends in Innsbruck and they try them. And this is an example of kind of like a plot that looks very similar to the video you've just seen. Just the x-axis is now time. You can kind of like still track kind of like the convergence with time. But this is an 8-qubit GHZ state, which they prepared in their lab, and they did the classical variation of this classical shadow procedure. And you can again see that it converges rather quickly. Okay.
So Richard, I think we're still seeing the slide of experimental demonstration. I don't know if you're changing the.
I changed. Kind of.
No, so we see the slide. No, we see the slide same with the title experimental demonstration, but nothing else. Yeah, sorry, yeah.
Do you see now a plot?
Yes, now this is what you were describing. Yes, yes.
Yes. So kind of like this is a plot that looks very similar to kind of like when I paused the video at the end. The x-axis is the number of shots. So this is a kind of like a summary parameter for time. And you can see that it converges again. You can see the fidelity, kind of the purity converges. This is now an 8-qubit GHZ characterization experiment. And we also tracked all two-body Rayleigh entropies to really show that this is a GHZ state, and we did everything in parallel. And if you look here carefully, the entire plot took 16 minutes to do. Kind of like if I kind of like convert 2,256 seconds, it's about 16 minutes. And this got the Innsbruck people quite excited because they had a seminal paper, I think roughly 8 years ago, where they did full state tomography of a GHZ state with maximum likelihood tomography. And it took them an entire day of measurements and 1 week of post-processing. Admittedly, they learned the full quantum state, which is more powerful than what classical shadows do. But as soon as you're interested in concrete observables, classical shadows are a valuable shortcut that allow you to get there quicker. And it's also particularly well suited for ion trap devices because their clock rate is slower than superconducting circuits. So ion traps are comparatively slow in producing shots. And with the classical shadow setup, you can do data processing while you wait for the next shot. And this kind of like really limits the time you have to spend as opposed to first collect all the data and then process all the data afterwards. So this is really kind of like a streamlining between the quantum computing time and the classical computing time. And with that, I want to kind of like go to the vignette application that I decided to talk about on very short notice, given the recent news about the Nobel Prize. And this also addresses kind of like a big vision I have for the future, what me and my team want to do. And the overall idea is to really use these classical shadows as a versatile quantum to classical interface, like a converter, and where we envision now an entire pipeline where on the very left, we have a quantum architecture of your choosing that is intended to prepare interesting quantum systems. And then we use the classical shadows to convert these interesting quantum systems into succinct data tables of bits. And then we can use these data tables to feed it into a powerful classical computer that maybe uses machine learning, with the hope to eventually learn a direct description of an underlying physical phenomenon. And the way we want to use quantum advantage is that the data is generated on a quantum device. And we have good reasons to believe that this data generation might be difficult for classical computers because classical computers struggle with simulating quantum architectures. And this is essentially a pipeline and a proposal to combine classical machine learning with a quantum architecture that prepares data. And this is a bit less ambitious than, for example, using quantum algorithms to speed up machine learning, but we really use the architectures the way they were intended. Classical computers are very good at machine learning, and quantum computers are very good at preparing quantum systems. So this is the overall vision. And the concrete example that I like very much was again done in collaboration with my friends at Caltech, mostly John Preskill and Robert Kueng, as well as Victor Albert from Maryland and Giacomo Torlai from Amazon Web Services. And this is now still kind of like a theoretical and numerical work. We don't have experimental demonstrations yet. We're working on this. But the idea is to learn something about ground states of quantum many-body Hamiltonians. And a good kind of like example is the antiferromagnetic Heisenberg model on a square lattice. What you see on the left-hand side is a square lattice comprised of 25 spins or qubits. And you can see that these qubits are connected, nearest neighbors are connected by a blue line of varying strength. And what we do here is we take Heisenberg coupling, so XX plus YY plus CZ, with a randomly selected coupling constant. So the left-hand side encodes a 25 qubit Heisenberg Hamiltonian where we chose the coupling strengths from, I think, -2 to 0 to ensure that it's still antiferromagnetic. And then if we make such a random selection, this is a 25 qubit Hamiltonian. And you can ask yourself, what is the ground state? Kind of like, what is the state vector that minimizes the energy of this Hamiltonian? And in the center, this is what we did. We used DMRG to diagonalize this Hamiltonian on the left-hand side, find the smallest eigenvector, the ground state, and then we record a correlation matrix where kind of like it's an n by n matrix where each entry tells you the two-body correlation between qubit I and qubit J. One of them is the row, one of them is the column. And we also used a Heisenberg coupling term, XX plus YY plus CZ, applied to the two qubits indicated by row and column. This is important because it's still kind of like, we can write it down classically. The underlying ground state is a 2 to the 25 dimensional vector where we don't have a succinct description. But this correlation matrix is succinct. And so this is now a well-posed problem. I give you the couplings on the left-hand side. There's, I think, 40 of them. I can store this. And I ask you about the roughly 25 by 25 correlation table, which is also scalable. And one way of doing this is DMRG, and you see it on the center. On the right-hand side is the result that we proposed in this project, which is exactly a learned classical function. So what we did on the very right is we used Amazon Cloud Computing Time. One of our collaborators was at Amazon, fortunately, to solve random instances, such random Heisenberg instances, let's say 10,000 times, get 10,000 descriptions of ground states, take the classical shadows thereof, and then feed these 10,000 classical shadows into a classical machine learning model that came up with a fully classical function where you can now input a new coupling table and you get the correlation matrix. And this is what you see on the very right. And I know it's very difficult, but visually they look very similar. So this is just a numerical demonstration that such an approach can work. And let us maybe kind of like look at this on a more general level. So kind of like this is the more general kind of like approach we had. We looked at the many-body ground state problem for a very specific reason, because there we have reason to believe that quantum architectures might help to cool down and actually get to ground states. This is a non-trivial problem, but I think a quantum architecture might have a chance at doing that. Whereas for a classical system, it's typically very expensive. It's not a difficult problem, but if I have n qubits, the Hamiltonian is a 2 to the n by 2 to the n matrix, and diagonalizing it takes exponentially many resources. And of course, there are smarter ways of doing that, like DMRG, but we also know that there's limitations, in particular, when we look at models that are two-dimensional or higher, like the one you've seen before. But so here's really a pipeline. I give you a classical description of a many-body Hamiltonian in terms of a lattice and coupling strengths. And I ask you about a classical representation of the ground state or certain ground state properties that I can store and check efficiently myself. I probably don't want to ask for the full quantum ground state, because then we would have to store exponentially many amplitudes, and this cannot be efficient. And the question is now how to get from the left to the right. And the standard way is direct computation, but this is expensive, and we strongly believe that it is expensive in the worst case. And so what we propose is to instead view this as a learning challenge, where kind of like the input configurations, the Hamiltonians, are random training data, and classical representations, efficient classical representations of the ground states, kind of like are the labels. And then we envision that we have access to kind of like many of these training data points with a random coupling XL and maybe a classical representation of the associated ground states. And then we feed it into a machine learning model, for example, a neural network, and train it to just learn the classical relation between Hamiltonian specification, which is classically efficient, and ground state properties, which is also classically efficient, like magnetization or correlations. And we propose to use classical shadows as an efficient way to store this training data. Kind of like just use a classical shadow of a certain length, because this is a data table which can be succinctly stored. And this is the added benefit that we can either choose to run expensive classical simulations to get the data, or maybe one day we can replace it with actual quantum architectures and use the classical shadow procedure from before to convert it into machine readable form and then feed it into this machine learning architecture. And we are theorists by heart, so we kind of like this idea, but we also set out to prove something about it, to give some rigorous kind of like performance guarantees. And then I don't know about you, but mathematical analysis of deep neural networks is a bit above my pay grade. I think I can maybe handle one layer, but like many layers is super difficult. But fortunately, there's a nice trick from 2018 or 2019 where people figured out that in the asymptotic regime of very many kind of like parallel, kind of like an infinite width neural network, where you have like many nodes in the middle and go to infinity, you can actually represent these neural networks by a kernel. And the kernel is a nice linear interpolation regime. So you can see the formula here, kind of like what a kernel does, it does linear interpolation on the training data you've seen already. So this is the formula for a general neural tension kernel. And you can also look at different kernels in order to make your life easier. But here for the experts, for those of you who have maybe worked with the ground state problem, and particularly those of you who worked with MPS, I know Spain is very, very strong here, is kind of like, here's also the key difference. Kind of like we use classical shadows, and they are a linear Monte Carlo approximation of density matrices. Okay, so we approximate the density matrix and not the pure quantum state. And we use Monte Carlo to do that, which is a linear sketching method. And so this entire process is linear, which also ensures that if I take a linear combination of classical shadows, it's approximating the linear combination of the underlying quantum systems. And this is very important for an ansatz like this. Whereas if you used MPS, you would have outer product, and a linear combination of two outer products of MPS is not an MPS anymore. And if I move to MPO, a linear combination of two MPOs with bond dimension D is not a bond dimension D MPO. But with classical shadows, you stay kind of like in the same data format. And this is like the one ingredient we had, which allowed us to kind of like mathematically tackle this problem, because classical shadows, the data format is invariant under linear combinations. And this allowed us to analyze these kernel methods rigorously. And I don't want to go into details, but the main theorem that we came up with 2 years ago is under strong physical assumptions on the underlying Hamiltonian and some scalability and locality assumptions on the classical observables we care about, namely locality. We could prove that this learning strategy actually works in a machine learning sense, in the sense that you achieve a small mean squared error over the distribution from which you sample the test and the training data. And we could also prove that the resources required to achieve a small mean squared error scale polynomially in everything. So the number of training data points is polynomial in the number of qubits. The runtime of training is polynomial in the number of qubits. And the cost of executing the learn function is also polynomial. So here's kind of like the main theorem, our first theorem in its full glory. And it just tells you that under strong physical assumptions, it works with polynomial resources throughout. the strong physical assumption we need is we have to assume that the family of Hamiltonians, I don't think about an entire, about one Hamiltonian, but about a parametrized family of Hamiltonians, and they have to have a constant spectral gap. This is a very strong physical assumption, but this is what we needed in order to make the theory work. And I think physically this means that you're deep in the phase, but still, kind of like we could show that if under these assumptions, deep in the phase, such a hybrid quantum classical machine learning approach can work with provably polynomially bounded resources. And a very smart kind of like Caltech surf intern student, Laura Lewis, did it one better and got an almost exponential improvement in the cost. So actually kind of like she could show that the number does not scale polynomially, but only logarithmically in the number of qubits. Again, on the strong assumption of a constant spectral gap, but still kind of like everything scales logarithmically in the number of qubits, which potentially opens the door to really go to big systems.
So one question, Richard, about this. I mean, you're saying that the constant spectral gap is a strong assumption, but presumably it might be necessary to make such an assumption.
Yes.
Yeah. Can you comment on that? Yeah. So you expect something like this is necessary?
Well, I couldn't figure out a way around it.
Yeah.
And just maybe very quickly for those of you who are experts, the way we actually prove that is reformulate this learning problem as an interpolation problem of functions. And if you assume a strong constant spectral gap, then you can use matrix perturbation theory to prove that if you wiggle the couplings a little bit, then the lowest energy eigenspace also only wiggles a bit. And in turn, the observables also only wiggle a bit. Whereas if you don't have a constant spectral gap, you can have eigenvalue crossings and then you can have like large disruptions. But this train of thought allowed us to effectively deduce that the function you want to learn is a slowly varying function in the sense that the gradient is controlled. And then you can use basic signal processing techniques actually. Because for a slowly varying function, we can do a frequency cutoff or a UV cutoff and then just randomly sample Fourier coefficients in order to get a good idea. And this is the strategy we followed in order to prove this. And I think this type of strategy somehow relies on smoothness and on establishing smoothness and slowly varying conditions. And I don't know how to do that without a spectral gap. Excellent question. Is there more questions or comments here maybe?
Yeah, not that I see. I'm not sure anyone is writing. So yeah, I think you can move on for now. Like I'll let you know if there's something.
Then now I think you can kind of like understand better what the motivating numerics was I told you earlier. You now understand the right-hand side. The right-hand side is such a trained function that takes new couplings and does a linear combination of the classical shadows it's seen already for the training data in order to approximate a classical shadow of a new quantum state that you haven't seen yet. And you can then use this classical shadow as a classical representation of the quantum system that allows you to reconstruct any type of local observables, in particular two-body correlations, which is the things we plotted here. And then we even went a bit further. We used some more sophisticated machine learning models. Here we don't have any theoretical underpinning, but if you, for example, replace these kernel interpolation models with a graph neural network, which is very well suited to kind of like learn the underlying graph structure of the lattice, then you can achieve substantial performance gains. And I find this very exciting. Our results are not conclusive yet, but I have the hope that we can use graph neural networks to train these lattice Hamiltonians on small systems and generalize it to larger systems. Because in a graph neural network, the graph itself is part of the input. But so far, kind of like, we cannot gauge the results in this direction yet. And then we did one more thing, maybe addressing a bit like Alvaro's question. Here is kind of like a Rydberg chain, a one-dimensional Rydberg chain, which is a very cool system. It's kind of like the systems that Misha Lukin, for example, uses to build, kind of like do his quantum error correction. And in this simple model, we only have two parameters. So it's kind of like a two-parameter region on the right, but it has three distinct phases. And here we just played around and kind of like violated the assumptions of our theorem to see whether it still works. And what we did here is we didn't restrict ourselves to a location deep in the phase, but we just crazily randomly sampled from the entire phase diagram. So we have data points from different phases and just ran our machine learning model on those. And they're kind of like star, cross, and diamond you can see on the right-hand side. We randomly selected for testing our model. And you can see the kind of like the plots on the lower side. And you can see that it works surprisingly well. So kind of like, I don't know why, but somehow the model still interpolates nicely, even if we sample from all the phases without distinction. And with that, I'm already done with my excursion into the realm of quantum data and classical machine learning. I think it's very exciting, and I think it's time to wrap up. And I want to be very brief. Here's the synopsis. I deeply care about the quantum readout problem because I think we need good, scalable, and easy to use solutions in order to really synergize quantum architectures well with classical hardware to get the best of both worlds. This is kind of like what me and my team are excited about. I presented you one way of doing that, which we call classical shadows. And again, it uses randomness, kind of like at each shot, kind of like we prepare the quantum systems, we do random single qubit rotations, then we measure the qubits, and we store the outcome and the random rotations we did, and then we repeat it with different random unitaries. And this is a succinct classical description that in a way covers information about all possible observables at once, and in a way that opens the gate for Monte Carlo approximation, which is scalable, parallelizable, and can be in an online fashion synchronized with the actual quantum experiment that produces the data points. And then I quickly told you about kind of like what excites me today, because I really think that we can use these classical shadows as quantum to classical interface to construct a pipeline where we use a quantum computer to generate data, classical shadows to convert it into machine readable form, and then classical AI and machine learning techniques to learn something new about the quantum. This is it. I now want to quickly use this opportunity also to advertise my team here in Linz. We're kind of like a new team. We call ourselves QUIC, Quantum Information and Computation at Kepler. We are 2 permanent researchers. Right now, a team of approximately 10 people. And we work exactly on these synergies that I told you before. We also delve a bit into art and science. And one thing that I'm very, very proud about is that we have a fair gender balance. More than half of our team members are female. And why do I say that? We have room and money to grow. If you're interested in these things, we have open positions on the PhD and the postdoc level. Thank you very much.
Okay, yeah. So thanks a lot, Richard, for the nice talk. Very clear. Yeah, I see some reactions. So yeah, so for the people in the audience, please write your questions in the chat, and I will be asking them to Richard. We have some minutes for that, so please go for it. Yeah, and maybe just to start this, there's something I'm a bit curious about. It's a bit of a high-level general question because I guess you can see this business of shadows and efficient tomography and so on as kind of a novel way of interacting with quantum systems. And I'm wondering if this is also a way for people, for instance, thinking of like condensed matter people working on many-body physics and so on, whether it's a way of coming up with new questions. New questions you can ask to different models, or new ways of looking at many-body physics, for instance. So basically the question is whether these methods can influence physics in any way.
Yes, I'm kind of like very interested in these topics myself. As you may know, I'm not a quantum many-body physicist, but I've been talking a lot to quantum many-body physicists over the last years. I find it exciting. And so far, the response by them was kind of like very intrigued. And I think several people are thinking in these directions.
Yeah.
If we get more technical, like one thing I think is very interesting is kind of like the relation between classical shadows and MPS and MPO. I think kind of like, I wouldn't say the classical shadows are better than MPS in no way, but I think they're just 2 different viewpoints on the same problem. And I'm very interested to learn when one maybe is more convenient than the other.
NPS meaning like when can you do tomography with NPS or just NPS
Yeah,
period?
exactly. Like if I have an NPS description, it's very easy to generate a classical shadow. The other way around, we have kind of like good theoretical papers from more than 10 years ago by Martin Plenio under the term of efficient NPS tomography.
Yeah.
But it's interactive and kind of like the actual algorithms are not as streamlined as they could be. Mm-hmm. So as a concrete research question, I think it should be kind of like easy, or it should be possible to have like maybe some DMRG sweeping intuition and use classical shadows to get an NPS.
Yeah.
But I don't know a proof that such a simple and scalable algorithm actually works. Mm-hmm. We do have more difficult algorithms that provably work with polynomial resources though, so we know that it can be done.
Yeah. Okay, any more questions for Richard? In the chat. Give it a second. I don't know if I can see when someone is writing, because at the moment I don't.
I think German.
Yeah,
German, you have to write that. You have to write.
One second, I'm gonna activate his microphone.
Okay. Yeah. So
now,
German,
I think you can speak now.
His mic is off.
Yeah. German, can you try to activate your microphone, please?
He's actually, if he's the German I think about, he's a floor below me, but I don't think I can I can be that fast.
No, he can speak now, but maybe, yeah, maybe.
Yeah, maybe it wasn't a question, just a cheer. Yeah. So no more questions. Okay, I guess not. So in that case, yeah, we can probably leave it as is. Yeah. So yeah, really, thanks a lot, Richard. I think it was very clear, and I hope people got something out of this and enjoyed the talk and the nice results that were presented here. And yeah, I guess that's it. So see you for the next time. And again, thanks a lot, Richard.
Thank you very much.
Adios.
Yeah.